Mute, share screen, and check the mic. His mic is good. Okay, supposedly the sharing is working. And it sounds like somebody got in. Yeah, I see. Good. All right. Good. So let's carry on here. So substitution cipher is one of the old ones. This is what you actually find in the Sunday newspaper. They change each letter to another letter. A goes to K, B goes to D. There's no simple pattern like moving all forward a couple letters in the alphabet or anything. And even this is so simple that 6-year-olds crack it really with a little bit of practice. The simple way to crack this is to just look for short words. I've got a word NA and FB and IQ. Well, those pretty much have to be to or as or so. You can pretty much guess where a the is, and that's one way to get in. Another thing is just to find the frequency. Frequency analysis is the most serious one. So, by the way, the exhaustive key search for a substitution cipher is very strong. The actual number of possible combinations are 26 factorial, which is 2 to the 88. If you really had to do a brute force attack on this cipher, you would not be able to crack it, even with modern computers. Even 2 to the 72 has not been cracked. There's a current attack against 2 to the 72 by brute force that is expected to last for 1,000 years. So this would be strong if you had to break it by brute force. The problem is there is a faster attack, and that's the problem why all cryptography is really shaky. All you can ever prove is that one particular attack takes a certain amount of time. You can never prove that there isn't a smarter attack, and often there is. And of course, the one that really works here is letter frequency. It turns out letters are not evenly distributed in English, not even close. E is very common, like 3% of all letters are E, or maybe that's even more than 3, I can't read it, it's a lot. I think it's like 12% of all letters, E, E-T-A-O-I-N. So if you have even a few paragraphs of text, you can pretty quickly find the E and the T. And once you do, you can pretty quickly find a word like the and get the H, and pretty soon it all just cracks. Yeah.
So if you, the last slide, if you were to say that, well, I'm going to have Q and X both map over to the same letter, so how would they change that number?
It would have, then effectively, I think it would go from 26 factorial down to 25 factorial if you knew that. And that is a common thing people did, was take, I think it was Q and X, a couple of rare letters and combine them into one to make it a 5 by 5 thing. That was a fairly common technique back in the old days. Yeah, but the, anyway, this is the important lesson here is you have to be good to every attack. There's a smarter attack where you do not have to try all possible combinations at all. You just have to try letter frequencies, and then you get several of the letters, and after that, it's very easy to crack all the rest. This is why you can pretty much do these in a few minutes on a piece of paper these days. All right, so the letter frequency attack, here you go. If you just look at it, the most common letter is Q, so if you put an E in there, then the first letter is a 2-letter word ending with E, which pretty much has to be we or he, and it doesn't take very long to crack all the rest. Yeah?
Looking at that, it seems that fair knowledge of grammar will help you, because if there's a D or an A, you just put that noun.
Yes, and by the way, most in this generation of encryption, which was done heavily in World War II and the Korean War, the standard technique called Fox schedules, my landlord used to do them, was to make 5-letter groups. So you eliminate the spaces between the words. That makes it much more secure. You can still attack it with a frequency attack, but you can't use short letters to get fast. By the way, another thing you can try is frequency of letter pairs. Like there are double O's, but there aren't any double X's. So counting pairs of letters is another way to get in. For that, you need a larger sample text. But if you have as much as a couple of pages of text, there's a lot of statistical techniques that will get you in. And they're all automated. In your first project, you use an automatic tool, Crypt tool, that will try these attacks. So if you want to crack these things and you're not interested in learning how to do it with pencil and paper, you can use online tools or Crypt tool, which is a Windows-based tool that tries the common attacks against these things. So that's the game. So now I have a Kahoot about this stuff. So let me bring it up. You go to kahoot.it, and I go to kahoot.com to start the game, but it is, let me sign in and go to my Kahoots. We are here at 141, this is the first one, so I play this one, And let me check my options. Look pretty good. Okay. So here's the instructions. And by the way, this should work even for remote viewers today because people tell me Zoom has no delay. When I'm up in that MUB building, the Cahoots don't work very well for remote viewers. So go to kahoot.it and join with that pin. And I'll see how many players I have here. Looks like I have about 20 or 25 students. So there we are. Here they come. Good. And it should work just fine on a smartphone or a tablet or anything. All right. But I think there's more than 11 of you. I'll wait a bit. Here comes more people. Good. I recognize this one. Fooled me before. He won, and I didn't think that was a student. When I saw password, I thought that was part of a website or something. I didn't. He fooled me with a name like password. That didn't look like a human name to me. So, all right. Now we're up to 16. Now I'm getting to know a few more. Like I know who DJ is, or whatever that one was. Hard B. I know that one. All right. You get to know people's fake names after a while. My grader's pretty good at this. There's always some people turning in their homework with the name of Hubcap or something, and she learns who they are. You know, so, all right. All right. Oh, good. I do have a pen. Cool. Okay, I'm up to 21. I'll wait maybe another 10 seconds, and then we'll go with whoever's gotten in. 6, 7, 8, 9, 10. Okay, here we go. And I should mention, if I don't know if you haven't done these before, these things, you cannot change your answer, and they grade you both on whether you're right and how fast you are. So to win, so it all matters. So it is more like a game show than ever. All right. So, are you ready? All right. So do you have a smartphone or a computer? I have a couple just so people can get started. Good, I got some answers, good. I can't change the timing or anything, I just let it go. 2, 1, I should have the sound, okay. So, that's right, so 20 people said yes, 2 people said no, which is kind of baffling. All right, so on we go. All right, they're doing it by smoke signals, okay. Nobody has any points yet. Next one's also no points. I just wanted to give people a chance to learn how to do it. That's right. That might be the best answer, really. Human consciousness is kind of deep and kind of complex. Okay. Right. Complicated is probably the best answer. Anyway. All right, now I think there's one with an actual point value. All right. No, you cannot change your vote because it's voting. It's grading on speed. So your first answer is it. So 8 symmetric is right. All right. And Blaine's the winner at the moment. So carry on. Which crypto system requires a secure key distribution channel? All right, that's symmetric. That's the problem with it. You have to distribute the key somehow. All right. How long would a brute force attack against a 40-bit key take? Yep, less than a day. This was CSS. This is the content scrambling system for DVDs, and it is really very easy to try all the keys. 40 bits is pathetic. That hasn't been secure in decades. So high is winning. All right. How long should a private key be? For reasonable security. Oh, I learned it at Cyber Patriot. The high school team, they used this. So I thought it was good. Better than the iClickers. And it goes to remote viewers. So it's better. All right. So the answer is 128 bits. The most popular one is correct. I see a lot of choice here. Let's talk about it. 100. I mentioned that a 56-bit private key has been cracked by brute force. And a 64 has, a 72 is not. So 72 is theoretically good enough. Anything in that range around 100 is good enough for a private key. I mentioned some people are paranoid, they go up to 256 just for room, but 2048 is way more than you need for a private key. Public keys are different. 2048 is what you need for a public key because public keys do not get to use all possible values of the key, only prime numbers, which are not that thick on the ground. 128 bytes is 8 times that. That's 1,024 bits, way longer than you need. And 56 bits is certainly not enough. That was cracked in the 90s. So I carefully did not put 256 here because 128 and 256 are both pretty good answers. Yeah?
There's some instances where a higher bit key would be not good.
Yes, the question is it possible the longer key is not better? And it is absolutely possible. In fact, a cryptanalysis by Bruce Schneier, who is one of the world's experts, suggests that AES 256 is in fact no more secure than AES 128. Because although the key is longer, you do fewer rounds of computation. So it is, and another thing is, doing more rounds of cryptography, just encrypting it again with the same routine does not necessarily make it more secure. You have to really look at the details. For example, if you do XOR and then you do it again, it undoes itself. If you do ROT 13 and do it again, it undoes itself. It is very often the case that just more rounds of the same cryptography is not better. You have to look at it carefully.
So there could be like some sort of anomaly that leads to like guessing the key.
Yes, and there certainly could be an anomaly that means that a longer key or a key of different length has a new weakness. And we'll talk about those. One of the ones to really worry about is padding oracle attacks. There have been a bunch of them against HTTPS, and you cannot use simple-minded common sense at all. You really have to do deep mathematical analysis. That's why I strongly say don't do it yourself. Use the standard stuff that the experts have chosen. Just assuming more of it is better is not true. Sometimes it is, and sometimes it isn't. All right. And I think, is that it? Let's see. 4 players just dropped their answer. Yeah, who knows? All right, here's another one. Okay, the second most common letter in English. All right, it's T. A popular answer. E is the most common, T is the second most common. All right. And I think there's one more. There you go. DNA uses 4 letters. How many substitution cipher keys are possible for it? You have an alphabet of only 4 letters. All right, 24 is the right answer because you start with the first one. You can choose any of the 4 to change it into. The next one, you can only choose 3. And the next one, you can only choose 2. So it's 4 times 3 times 2, 4 factorial, which is 24. That's why 26 letters, you get 26 factorial, which is a big number. There are only 24 possible substitution ciphers for a language with only 4 letters. Yes. But there are 2 strands of DNA, and the other pair is just a copy. So you can have any pattern of letters. You're not required to have certain patterns of letters in real DNA, which, by the way, is more relevant to computers than it used to be. They recently found out that you can put they put like an image in DNA, and they even put a virus in DNA now. So, I mean, there is now DNA computing. The thing about it is it's very slow. But there's been science fiction for a while talking about how if you look in the DNA, you might find like a brand mark from God or whoever made us, and we're almost to the point where we can do that. Whether anybody did it to us is not clear yet. But when we make artificial life, which we already have, by the way, we had artificial life for a while, very simple single-celled things they made, then we can put trademarks in it and everything. Anyway, so the winners are Cam, High, and Ward. You will obviously have to tell me later who you are. But that's fine. All right, so let's go back to the slides. I think, good, we're not too late yet. We can carry on here. So, modular arithmetic, this is a little bit of math you learn here. Modular arithmetic is extremely important. This is almost all modern cryptographic systems use it because you want to control how big something is. You don't want the encrypted thing to just get bigger and bigger without limit. So you use circular math called modular arithmetic. And you've been using it all your life. This is what clocks are. If it's 3 o'clock and you wait 10 hours, it's not 13 o'clock, it's 1 o'clock. And if it's 2 o'clock and you want to meet 3 hours before that, you go back to 11. That's modular arithmetic. You have a circle. So all the numbers just roll around. And that's the game here. So they write it down this way. If I have 3 mod 9, or if I have 12 and modulus is 9, then that's equal to 3. Because you have 9 go around once and then 3 more. If I have 37 mod 9, then 36 is an integral multiple of 9, so that's equal to, I thought it was equal to 1.
Yeah.
Yeah, this is like a typo or something, huh? Anyway, 37 mod 9 is 36 plus 1, and all integral multiples of 9 do nothing, so 37 mod 9 is 1. You can have negative numbers. If you have minus 7 mod 9, it's minus 7, it's also equal to 2. You can add any number of 9s to it. And there are many numbers that are identical. Minus 7 equals 2, it also equals 11, it also equals 18 in modular arithmetic. By convention, you choose the lowest number that's positive and call that the standard answer, but the others are just as good. The same thing is true of square roots. The square root of 4 is 2, and it's also minus 2. Both of them are perfectly fine. By convention, we usually refer to the positive one, but there's nothing wrong with the other one. And in modular arithmetic, there are an infinite amount of every number that are the same, because there are only 9 numbers. So you just think of it like a clock, and we'll play with that a bit. So the remainder is what they call it. You divide it, you take 12 mod 9, you divide it by 9, and you take the remainder. So 12 is 1 9 plus 3. All right, 21 is 2 9s plus 3, 18 plus 3, and minus 6 is kind of hard to do by division, but if you add 9 to it, you get 3. And you can add any number of 9 of the modulus to it without changing the number. So I'll have a few things where you practice that, but you get used to this modular arithmetic thing. You just go around a circle. This is the way all computers are. This is there was a CTF last weekend, and there was a game there that relied on this. As you probably know, if you have computers and you have a number and you keep adding and making it bigger and bigger, after a while it rolls over and becomes negative, because computer math is all modular. You only have so many bits, like 16 or 32 bits, and after you go too high, it rolls around, just like the car odometer, which is also modular. In fact, pretty much anything you really build out of real hardware ends up being modular because you only have so many bits. At some point, you lose bits, and it wraps around. All right, so like I say, the smallest positive integer is what you typically take. So 12 mod 9, you call it 3. You don't call it minus 6 or 12, although those would be fine. Typically, you call the result the smallest integer. All right, now division gets really screwy here. How do you divide modularly? And the answer is you multiply by the inverse. And inverses do not always exist. This is the dirty trick. So let's take 7 mod 9. 7 mod 9 is 7, okay? Because that's the slowest, that number less than 9. But if you take 7 times 4, you get 21. 28, which is 27 plus 1. Okay, so 7, consider 7 times 4. That's 28. That's 27 plus 1. So multiplying it by 4 gets you back to 1. So if you want to divide it by 7, you multiply it by 4. Because 4 is the inverse of 7. This may seem a little maddening, but that is how it works. And realize this is something that was real painful for me at first, because I grew up as a kid learning addition, subtraction, multiplication, and division as if they were fundamental things, but they are not. They're really nothing more than sort of cryptography. They're just a way of converting a number to another number, and it's really quite arbitrary. So in a modular arithmetic, you can define multiplication and division as just a way of turning a number into another number. And you have to. And the fact that I'm used to it in the real space or the integer space doesn't make any difference. Modular numbers, you can define similar functions. And this turns out to be important as you go ahead. The cryptosystems are just a way of mapping numbers to other numbers. So you have an input plain text message, you change it to other numbers. You just have some way to change it and some way to change it back. That's all we're looking for. Yeah.
So these are also apply to like binary or hex?
Yes, you can express them all in binary or hex or any other system you want. And that's probably what we're going to do tonight in the binary games. So this is as far as the math goes in this course. I want you to learn modular arithmetic. We'll practice it a bit more probably next time. And binary and hex and greatest common division. This is the first time you've seen it. We'll go over it. Each class we're going to do a little bit of math. So, all right. Here is another fun fact. If you want to take 3 to the 8 mod 7, sorry, I'm a little messed up here. All right, you could multiply it up to 6561 and then divide it by 7, and that is really the hard way. If what you can do that is a whole lot easier than that is you could break it into 3 to the 4 times 3 to the 4, and that's 81 times 81. And each one of those can get the modulus separately. So 81 mod 7, let's see, I don't know if I can even do that in my head. Yeah, apparently it's 4. 72, I don't know, I tried to do it in my head. What's 70? Oh, 70. 77. Okay, so 77 is 7 times 11, so 81 mod 7 is 4. So 4 times 4 is 16, and 16 mod 7 is 2. Because yes, 14 is 2 sevens. So the point is, if you have a big number to do modulus, and it's composed of multiplying other numbers together, you can take the modulus of these separately. This is very important because it means you can do the modulus of very large numbers very fast. And in the projects you'll get here, when we go to Python, there are 2 ways to write modular arithmetic, and if you do it one way, it takes forever, and if you do the other way, it's instantaneous. So there are more of these will come up. There are smart ways to do calculations that are fast. Yeah?
So that seems that the regular rules of exponents apply. Yeah.
They do apply, yes. So AB mod something is A mod something times B mod something. It just, the associative law works.
And the division would do the same exponent. Right?
Well, division you do by multiplying by the inverse, and then the same rule applies. Yes. Yes. And we'll practice this stuff, so brothers, you don't worry about it too much. Anyway, they call this a ring. Capital Z is the mathematical symbol for a ring, and ZM has M entries, usually 0 to M minus 1 is how you do it. The clock up there goes from 1 to 12, but in cryptography, you typically make it go from 0 to 11. Anyway, that's the game here, and here's the special laws that apply, which I'm not going to go into any detail about here. The point is, that's how we do them. These are the rings. So let's talk about the Caesar cipher. We talked about this one. So Caesar cipher is where you just shift things forward. So you take numbers and you turn letters into numbers. The usual way is 0, G is 25, and you just add numbers to it. So attack is here. You just add 7 to each number. So 0 plus 7 is 7. 19 plus 7 is 0. Because it wraps around off the 25 and comes around because you're doing modular arithmetic. This is 7, 2 plus 7. Yeah, this example is pretty awful, isn't it? Anyway, that's what I get for using somebody else's slides. They actually only have 5 letters in the answer. That's kind of cruel. 2 plus 7 is 9, and 10 is 17. You're missing a 9 here. Anyway, you just shift it forward by a few. When I was a kid, this was the Captain Crunch decoder ring. Yes, that's right. Anyway, so there's a mathematical description. The key X and Y are from 0 to 1, 0 to 25. Encryption is adding it, mod 26, and decryption is subtracting it, mod 26. That's all. You shift it to one way to encrypt, you shift it back the other way to decrypt it. It is not secure because the key only has 26 possible values. So you can do a brute force attack of all 26 values. It's very easy. So the Caesar cipher is fantastically weak, trivial to crack. But you can improve it. And the affine cipher uses two numbers. Instead of just adding a constant number to the key, you add it, and then you also multiply by the key. So you have AX plus B. X is the plain text. You multiply it by something, and then add something else. So there's two keys, A and B. And both of them, I think, go from 0 to 26. So you end up with a key space of 312 possible keys here. So that, again, there are several attacks. You can do frequency analysis like before. The brute force attack would take 312 tries, but there are ways to do it faster with frequency analysis and so on. Anyway, so this is what the lessons of this should be. Never develop your own crypto algorithm. We're going to run a few of these simple mathematical things, but unless you want to be one of the 10 smartest people on earth if you're going to develop cryptography, because there is no use for C-graded cryptography. Just copy the experts that have invented it. And here's the practical stuff to learn. You always look for the weakest spot, which is what the cryptanalysts do. For practical for us, 64-bit is not strong enough for pretty much anything. 128-bit is essentially uncrackable right now, but we're worried about quantum computers and such, so 256 is used by some people in the pious hope that it will stay unbroken for a while. Nobody knows how long it will last. There is an argument that 128 should last forever. If you like science fiction and mind-bending, every computer calculation adds to the entropy of the universe because it burns some gas, essentially. And the entire universe is not infinite. We know how big it is, about, I think, 50 billion light years across. The total amount of available entropy in the entire universe is less than 2 to the 128 bits. So if you powered all the computers you could ever build in the whole universe until the end of time, you couldn't try 2 to the 128-bit keys. So there's an argument from physics that 128 bits should be enough. However, there is a theoretical computer that is called symmetric or something, where for every bit that flips here, another bit flips the other way here, so it doesn't increase the entropy of the universe. Nobody knows how to build it, but if you built one of them, that rule wouldn't apply. So anyway, you have to go into the world of science fiction and mysticism to guess about this. You're trying to guess what's going to happen in 20 or 100 years. Good luck. We might just all be dead, and then you won't really have to worry about your cryptography anymore. Yeah.
Rather than put so much energy into trying to crack all these bits, why not just focus on social engineering?
Absolutely.
Grab somebody at wine and dine, torture them with.
Well, this is a very good point. I'm glad you said, well, I just use social engineering. That's the point. All cryptography can ever do is close this door, and then attackers will come in through another door. So you have to have, cryptography is just one aspect of security. If your cryptography is weak, then people will just steal your signals off the wire. You want to keep your cryptography strong enough that they have to use other techniques like social engineering to get your secrets. And then you try to have other defenses for those. And that's how we are. That's why I say, you know, even if the quantum computers wipe out everything we've got, we'll just come up with something else and limp ahead because we're already using insecure, less perfect techniques to protect us from those other attacks like torture and social engineering and stuff. You just have, that's why nothing's perfect. And it's all a game of picking something that, that you can stand and making it as good as you can. So let me see if I figure out how to get, there's the results. What's that? No, social engineering is in the other classes, more or less. So I'd like to go back to Kahoot.com, which I think is, here it is, good. All right, so here's the next Kahoot. And then I think we'll do a little bit of ordinary math. All right, so this one, let me check my options. The first time I did this in the other class, I forgot to randomize the answers, so it was always A. And a few people figured that out, so I try to make sure I've at least randomized the answers. Okay, good. I think this one is not going to be that bad. All right, join. There we are. It's coming. There we are. 160018 is the number. And then I've got a few binary games to give you. And I'll go over that modular arithmetic next time. I didn't like my slides much. I'm going to make some better ones. Try to explain it more clearly. 10 minutes. Well, that's probably going to be enough to do the Kahoots. They don't take long. All right. 21 players. I'll wait another 10 seconds. There we go. See, I'm influencing people. Someone's name is now Hubcap. All right. So, how large is the key space for the Caesar cipher? All right, 26. There are 26 possible shifts. You might argue 25. Anyway, doesn't matter. That's the key space. Good. So Patriots are winning. How about the substitution cipher? All right, 2 to the 88 is right. That's a very large key space. Not 26. There are many possible ways to substitute A to B, A to C, A to D. So if there wasn't a shortcut, it would actually be a very good cipher. What's 9 mod 12? All right, it is 9, which is not even the most popular answer. So mod 12 means the numbers go from 0 to 11. And if you go to 12, it wraps around to 0, so 9 is just 9. If it was a bigger thing, like 13, 13 would wrap around and turn into 1, from 0 to 1. So all you do is put the numbers around a circle. So let me just make an attempt to explain it, and I'll do more of this next time. So 12 means you have 0, 1, 2, 3 around a ring, and the last one is 11. So 10 and 9 is just right there. So 9 mod 12 is 9. But if you had 13 mod 12, it'd be 11, 12, 13. It would be 1. 14 would be 2, and so on, all right? Just like military time on a clock, except you start at 0, unlike the clock. Although military time actually starts at 0, but that's another issue. All right. The answer is 9. 9 mod 12 is 9. It's 9. Yeah, because since the mod is 12, you have numbers all the way up to 11. So 1, 2, 3 up to 11. You take a modulus 12, they just stay the same. The only things that change when you take a modulus is things that have gone more than one turn around and wrapped around. So mod 12, all the numbers from 0 to 11 do not change. All right, let's try this one. 44 mod 10. All right, good. The popular answer 4, because you take away multiples of the modulus. Take away the 40 and throw it away. 4 is what's left. You divide by the modulus and keep the remainder. So people are getting it. Like I say, I'll have a more orderly presentation of it next time. My explanation wasn't much good tonight. I'll try again next time. How about this one? The multiplicative inverse of 3 mod 5. That's a little tough. All right. The most popular answer is correct, which is 2. Let me just talk about this one, because this is a little bit mind-bending. So first, let's make a ring for modulus 5. So if I put 0 here, 1, 2, 3, 4, that's it. There is no 5. There are 5 total numbers. 5 is 0, 6 is 1, okay? Now I'm going to take 3, and I want the multiplicative inverse. So the inverse of 3 is the number which, when multiplied by 3, gives you 1. So the simplest thing is just try these values. 1 times 3 is 3. That's no good. 2 times 3 is 6, which is 4, 5, 6. 2 times 3 is 1. So 2 is the inverse of 3. It may seem nuts, but multiplying something by 2 will undo multiplying by 3 on ring arithmetic. So if you multiply something by 3 and you want to get back to where it was, you multiply it by 2. And you can perhaps get an idea how important this is going to be. Multiplying it by 3 might be encrypting it. Multiplying by this would decrypt it. So you need to find how to reverse it, and that's the game. 3 times 3, what's that? 5, 6, 7, 8, 9. 3 times 3 is 4. 4 times 3 is 12, so it's 5, 10, 11, 12. So 2 is the inverse. 3 and 4 aren't. Okay? It is not very complicated. The only problem is you imagine you already know what multiplication is. And this flies in the face of your intuitive grasp of normal multiplication. This is, in fact, all that other multiplication is. It's just an arbitrary way to turn numbers into other numbers, but we've forgotten that and imagine it has some reality. None of it has any reality. All math is just an arbitrary game of moving little chess pieces around. And this is just another system of it, but you have to think a little more abstractly, and it just takes a little getting used to. Yeah?
How does the system work with decimals?
You cannot have fractions in modular arithmetic. That's a very good question. You can't have floating points, only integers, because there has to be only so many values around the ring, n, and it's an integer. You can't have modulus pi. It's got to be integers. This is, number theory is all integers. Very important issue. I'm glad you brought it up.
Quick question.
Yeah.
For the ring,
Yeah.
to determine the size of the ring, like you have 0 and 4 centers.
That's modulus, yeah. The total of,
That's the modulus size.
that's the modulus, the total number of things. So it always goes from, if modulus n, it goes from 0 to n minus 1. Okay. And like I say, I'm going to make a more better presentation of this for next time. It's kind of garbled today, but it's your first chance to see it. All right. I got a couple more things here. There. What's the multiplicative inverse of 4 mod 9? Okay. All right. It's not the most popular answer. 7 is the right answer. So let's talk about this. And the easiest way to do this kind of question is to just do it by trying every possible answer. So let's make the ring. We're doing mod 9. So what's the highest number on my ring? 8, right? 8, 7, 6, 5, 4, 3, 2, 1. That's my ring. Okay, now I'm taking 4. And here's my choice. Let's take 4 times 1. Well, that's 4, so 1 is out. I'm trying to find something which, when multiplied by 4, turns into 1. 4 times 2 would put me here. 4 times 3 would put me here. I could even just count around. Here's 4 times 1. Go 4 forward. 4 times 2, 3, 4, 5, 6. Well, I got to count by 4s. I'm counting by 3s. Anyway, 4, 1, 2, 3, 4. That's 4 times 2. 1, 2, 3, 4. That's 4 times 3. That's 4 times 4. 4 times 5. 4 times 6. 4 times 7. So 7 is the multiplicative inverse of 4. And you can do it mathematically. 4 times 7 is 28. Now, I've got a modulus of 9, so 3 times 9 is 27. And you can subtract any amount of 9. So you subtract 27 from 28, you get 1. So 28 mod 9 is 1. Let's write it here, and we'll get used to this in future classes. That is 1. Because 0 mod